Welcome everybody, welcome back. We finished off on Wednesday talking about this principle of data reduction. We want to go from a sample of n observations and we want to reduce this to a statistic, which typically is just some sort of function of my sample, which has a much smaller dimension. And we want to perform this sort of transformation without losing any information about theta. And what we spoke about were these sufficient partitions, which we defined as those such that the probability of x taking particular, or the sample taking the particular values x equals x, given that I'm in a partition AT, does not depend on theta. Essentially, it says that once I know I'm in a particular set of my partition, the actual values of x don't tell me any additional information about theta. It's all contained in my sufficient partition. And we usually define these partitions through a suitable statistic. That is, if I'm looking at my sample space, this script x, and I observe some value within that set, well then the sufficient statistic is equal for all the samples within inside this set, say A1. And I don't care where exactly I am inside of A1, which means I don't care for the particular values of all my observations. I just care about the value of the sufficient statistic, and in this case, they're all equal to the same value, Tx. So let's look at an example of applying this with our Bernoulli example, which we've sort of seen before. So let's suppose that we have n IID Bernoulli observations, where we have theta is the parameter of a success. The probability mass function is given by this expression here, right? So it takes theta if we observe a 0 and 1 minus, it takes the value theta if x equals 1, and it takes the value 1 minus theta when x equals 0. So theta for a success, 1 minus theta for a failure. Now the partition, script A, which equals A1, A2, A0, A1 up to AN, where x is an element of AR, means that we have R successes. Okay, so if and only if we define this statistic, the sum of the xi's equals R is sufficient for theta. So here I'm defining my statistic to be the sum of the 0 ones, or the number of successes. And that's why my partition goes from A0 to AN, because out of n trials, the smallest amount of successes you can have is 0 and the maximum is n. Another way, instead of talking about a sufficient partition, we can talk about a sufficient statistic, and it's just the statistic that defines the sufficient partition, which here is just the sum of the xi's. All right, so let's show this by applying the definition of sufficiency, which is on the previous slide. We have to compute this conditional probability and show that it does not depend on theta. Then it says that my statistic t is sufficient for theta in that example. So this example doesn't show us how to obtain the sufficient statistic, but here I'm just going to show you that indeed this t is a sufficient statistic because of this conditional probability doesn't actually depend on theta. All right. We want to prove that the sum of the 0 ones, or the number of successes, is sufficient in the Bernoulli case, and we're going to apply the definition of sufficiency to do this example. So the proof follows from the original definition of sufficiency. Okay, which is that conditional probability statement. We're just going to compute that for this example. And as I said, this doesn't show us how to find them, but I'm telling you what it is and shows that it actually holds this definition. Our goal is going to be how we can actually come up with these sufficient statistics. We have the following partition, right? Because we're talking about sufficient partitions. So if we're inside this partition, we don't lose any information about theta, given that I observed a particular sample that lands inside that partition. And it's created by my sufficient statistic t. Right, so we call this script A, and as I said, there's only n+1 sets. We only have 0 to n successes. I can hear someone's microphone. Do you have a question? I'm just going to mute that so it's clear. Okay. Please make sure you only put your microphone on if we're going to say something. Now we define each of these sets inside of my partition, script A, are all the samples x, such that the sum from I equal 1 to n of xi, i.e. the number of successes, takes the value r in the subscript, and this holds for r equals 0, 1, all the way up to n. Now we're going to look at the definition of sufficiency, which means to look at the probability that x equals x, given that x belongs into a set in my partition, which here just means the number of successes equals r. Here we apply our conditional probability law, so this is like A given B. Well, it's the joint probability that x equals x and the probability that x belongs in the set AR divided by the probability of what's in the condition, and that's x belongs to AR. And I'm just going to call this star. So what we have to note here is that when I say that x belongs into the set AR, this means that the sum of the observations, or the number of successes, takes the value r, and we can actually compute the distribution of this guy, right? Because xi are Bernoulli, and the sum of Bernoulli turns out to be binomially distributed. Yeah, so this is like a basic statistical knowledge. The sum of Bernoulli is a binomial experiment, and we now have the distribution of, well, this expression here. And I can write this more formally, that the random variable, the sum from I equal 1 to n, well, this guy is distributed according to the binomial distribution. We have n trials, and we have the same probability of success being theta. I'll leave that conditional probability there, right? Right, what is this saying? i.e. the sum of Bernoullis is binomial. Right, this is sort of just by definition. Sum of Bernoullis has a binomial distribution. Okay. So this is going to help us to compute this conditional probability here. Now, we know the probability mass function for the binomial distribution. Right? It's the probability, I'm going to use the notation of the denominator, that we have r successes. Well, this is just the probability mass function for a binomial, which is n choose r. We have r successes, and the remaining ones must be failures, n minus r. And of course here r can only take the value 0 to n in the binomial context. That's just writing down the probability mass function for the binomial. Now we can go back to my conditional probability, right? A probability that x takes the value x, right? And that's a vector of values. And we know that x belongs to the particular set of my partition. So this is in the numerator, essentially. Now I'm going to break this up into two cases. If the sum from I equal 1 to n of xi does not equal r, then this probability has to be 0. Why? Well, x doesn't belong to AR because the sum of the xi's does not equal r, so this event can't happen. And the probability of an event that can't happen must be 0. On the other hand, if, no, we've got too many ifs here. If the sum from I equal 1 to n of xi does equal r, then it's just the probability, then this is already satisfied. So it's just the probability that x equals x. And we know that that's just theta to the sum of the xi's into 1 minus theta to the n minus the sum of the xi's. Okay, from I equal 1 to n. Now it just follows as a product of these probabilities. Right? It's a product of this probability mass function n times because we have that IID assumption. All right, so that gives me the probability in the numerator. And now I can plug this expression in the numerator. I have this expression for the denominator, and we'll see what happens. We ideally want this expression not to depend on theta to show sufficiency, right, by definition. So let's compute that conditional probability by using the two facts that we just discussed there. Right, so therefore the conditional probability in what we called star, well, we have the following. It's the probability that x takes the value x, given I know that x belongs to the set of my partition AR or R successors. Again, we still have the two cases. It still takes the value 0 if the sum from I equal 1 to n of xi does not equal r, because this is 0, and that's in the numerator in this case, so the whole thing's just 0. And for the denominator, the other case, when it does happen to equal r, well, it's this expression divided by this expression, or it's theta to the r, 1 minus theta n minus r, divided by, well, this guy, n choose r, theta to the r, 1 minus theta to the n minus r. Okay, because the sum of the xi's is r in this case, so I can just replace that summation with the letter r. Okay. What is the star in this case? That's the equation I just wrote up here. That conditional probability is the star, which we use for the definition of sufficiency. Now what do we see? We get a bunch of cancellations, and we're just left with 1 over n choose r, right? Theta has completely disappeared from this expression. Right, so the probability that x belongs into the set AR, so given that information, the actual values of my sample don't tell me anything more about theta. So all the information is contained in the fact that I'm in a particular set of my sufficient partition. Yes, so the question is basically it's sufficient because this conditional probability doesn't depend on theta is correct. All right, so the conditional probability, this isn't the general way in which we'll show sufficiency, but this is how you would do it if you wanted to do it by definition. We're going to find other ways in which we can actually find why the sum of the xi's is a sufficient statistic for this example. Okay, here I've just told you that that's the case. All right, so this conditional probability does not depend on theta. Hence, we must have that T of x, which is the number of successes, the sum from I equal 1 to n of xi is sufficient for theta. Okay. Any questions on that one before we move forward? Yeah, okay. Let's just sort of recap what we've discussed about sufficiency so far. Given the observed value of the sufficient statistic T, we know that the observed value of x is in the partition set AT. So in that previous example, I don't care the sequence of 1s and 0s. As long as I know that their sum of the 1s and 0s equals r, then I'm in the set AR. That tells me all I need to know about theta. And translating that back into the previous example. And sufficiency means that this conditional probability is a function of x and t only, i.e. it's not a function of theta. If we look back here, this conditional probability was only a function of, well, t in this example, right? The r, which is the number of successes. Okay, so it only depended on t, not theta. And this is the key idea of sufficiency. Once we've observed the particular realization of my sufficient statistic T, knowing the particular values of x do not help to better identify theta. And so I can do all my inference based on the sufficient statistic t. And we also arrive at this notion of the sufficiency principle, which is referring to two samples, x and y. And if t is sufficient for theta, so t is my sufficient statistic, then if I have two samples, x and y, such that their sufficient statistics are the same, so when I apply t on x and apply t on y, they're the same, then my inference about theta should be the same, whether or not I observe the x sample or the y sample. Okay, so again, just sort of looking at if this was my sample space, and then I knew that this was my partition set A1, and this was x, and that was y, and I knew that tx equals ty, then my inference should be the same because all the information is contained in the fact that I know I'm in the set A1, right? That's what sufficiency says. There's no additional information knowing where I am in the set A1, just that I'm in the set A1 is all I want to know, or all I need to know to say something about theta. Okay, so they take the same value, say maybe T1, for example. And so this set A1 is defined as all the values x, such that the statistic t of x takes this value T1. Okay, and you do that for all other until you finally partitioned your whole sample space x of observations. Okay. So the idea to search for these sufficient statistics makes sense because we reduce the dimension of our observations from n down to the dimension of the statistic t. And given two separate samples y, if their sufficient statistics are the same, then the inference I should draw from them should also be the same. But how do we find a sufficient statistic? How do I know that the sum of the observations is sufficient for a particular distribution? Well, there's a very important theorem called the Neyman-Fisher factorization criterion, which enables us to find these sufficient statistics. The theorem says that if xi is distributed according to f, where f is some family of distribution parameterized by theta, then the statistic tx, right, it's just a function applied on my sample. Well, it is sufficient for theta if and only if, so there's two statements to say, that says if it's sufficient, then I can write my likelihood, so my Lx theta, which is just the joint density of my observations, in this form. And also, if I can write it in this form, then it's also sufficient. So there's two things to show there. And the form of the likelihood is it takes two functions, g and h. Now, g takes two arguments, the sufficient statistic and the parameter theta. And then it multiplies by a function of just my observations. Okay, so essentially what this is saying is that my likelihood only depends on my parameter theta through the sufficient statistic t. So wherever I see a theta, right, there must be a tx, or there's a tx attached to it, right? The likelihood only depends on theta through the sufficient statistic, and then whatever's left just can go into this h of x. Okay, so if I can write it in this form, then that says that my t of x must be a sufficient statistic for the parameter theta. Right, so it gives us a nice procedure, right? We write down the likelihood, Lx theta. We then try to factorize the joint distribution, or the likelihood, into a product of these two non-negative functions, g and h. One function, g, which may depend on the parameter theta, but depends on the sample only through the value of the statistic t, so g of t theta. Whereas the other factor, the h, does not depend on the parameter theta, and it only depends on my sample. Right? So it gives a nice general procedure. Write down the likelihood, try to express it in this form, and then I know that tx must be sufficient for theta. All right, let's see why this happens to be true by going through its proof. So as I discussed, there's two things we need to prove for the Neyman-Fisher factorization criterion. All right, we need to say, okay, if the likelihood can be written in this form, then t must be sufficient for theta. So this is sort of the reverse proof of the theorem. So going from this likelihood expression, then saying t is sufficient. Oh, sorry, I've moved it off the screen. Okay, good. Okay, and then you can go the other way. If t is sufficient, then I can write the likelihood in this form. Okay, so there's two ways you can do that. And that's the second one. T is sufficient for theta, then I can write the likelihood in this form. And that's the implied part of the theorem. Okay, so when you see sort of if and only if statements, well, there's two directions to prove. There's the implied part, and then there's the implied by part. All right, so let's start with one, which says, if I can write my likelihood in this factorized form, then t must be sufficient for theta. All right, so let's assume that we can write the likelihood into this form. So a function g, which depends on the sample only through the sufficient statistic, and theta times just some function of x. Now, to show sufficiency, we just have to check that t is sufficient for theta by considering the conditional probability. Oop, this guy here, and show that it doesn't depend on theta, right? That's the definition of sufficiency. I assume I can write my likelihood like this. Now let's show that because my likelihood has this form, this expression doesn't depend on theta. And it follows similar steps to the previous exercise. Here we just apply the definition of conditional probability. So it's the probability that should be the other way around. X equals x and t equals t divided by the probability in the condition. Now again, if t of x does not equal t, then this event can't happen. So the numerator has probability 0, and so the whole thing's just 0. On the other hand, if tx does equal t, then this event has occurred with probability 1, and so we only have to consider the probability that x equals x divided by the probability that t equals t. Okay. Clearly, this first case doesn't depend on theta, so this is fine. Now let's sort of look at the second case. We know we can write the likelihood as this product of some gt theta times h of x, and that's exactly what I've done in the numerator. These are the same things, right? The likelihood or the joint density of my observation, they're the same thing. And so I can just write this expression here. Now in the denominator, we're saying that t must equal t. Okay, so that says so one way to write the probability that t equals t is to look over all, say, x tilde, such that t of x tilde equals t. And then we look at the probability that x equals x tilde. Now, what it says is, to compute the probability that t equals t, I search for all x such that t of x equals t, and then I sum all these probabilities. That gives me the probability that t equals t. Right? So here it's just the probability that x equals x, but I don't want to sum over all x. I only want to sum over the x that leads to t equals to t, because that's the probability I'm interested in. And let's call all the x's such that tx equals t is x tilde. So I'm summing over all x tilde such that tx tilde equals t, and then summing over all them probabilities. And that's what I've written in this expression here. Okay, because probability x equals x, again, can be written as this form here by definition. But what changes is here in this last x, it's x tilde, because that's what we're summing over. It's this x tilde as the argument. Now we get some cancellation. This is a constant, so it can actually come out in front of the summation, right? Or it just cancels with the one on top. It's just a constant with respect to x tilde. It doesn't depend on x tilde. It just depends on the value t, okay, which is constant in this case. And so the g's cancel, and so now we get this ratio here of h of x, and then this summation of x tildes of h of x. But guess what? There's no theta in any of these expressions. Remember, h is free of theta in the top and the bottom. And so it does not depend on theta, i.e. it's independent of theta, and hence t is sufficient for theta. So what we showed this is that if I could write my likelihood in this form, then this conditional probability doesn't depend on theta, and hence t must be sufficient for theta. Any questions on the first proof there? Yeah. Sorry if this is x sufficient for theta as well? No. So x is my observations here. So you mean the whole sample? Yes, the whole sample is sufficient. Yes. Yes. Yeah. Sorry. Yes, of course. But there's no data reduction there. And so it's not useful for us. But yes, the whole sample itself would be sufficient. Yes. because this conditional probability wouldn't depend on theta, right? Probably x equals x given x equals x, so it's just 1, which doesn't depend on theta. Yeah. Okay, now let's do the second proof that says if t is sufficient, then I can write the likelihood like this. Right? So it's the opposite way of what we did before. And this one's a little neater. Okay, so assume that t is sufficient. Okay, so remember what that means. That means that the probability that x equals x given t equals t is free of theta, right? That's what that means. So we're going to assume that's true. Then this is just my likelihood of x. Okay, the probability x equals x. Now what I'm going to do is I'm going to add a sure event that t equals t of x. Now this is a sure event since t is sufficient by the original assumption. Okay, so t must equal t of x. So this event is definitely occurring. So I can add it into this expression. Kind of opposite what I did before. Before I kind of reduced it by looking at two different cases. Well, here I'm just in a case where this has definitely occurred because t is sufficient. And so I can include it in this probability without changing the probability because I've added a sure event. And by sure event, I mean it occurs with probability 1. So now I have a joint probability of x and t. Well, we can apply our conditional probability laws going the other way. Here I'm missing a p. So we can say first, what's the probability that t equals t? And then multiply that by the probability that x equals x given t equals t. Now, we know that this expression here is free of theta. Right? That was by this t is sufficient. So this function here is like my h of x. Right? Doesn't depend on theta by definition of sufficiency. This guy here depends on t and still depends on theta. Okay, so you could put a subscript under the theta there. All right, so this first function is like my h of x, and this guy is like my gt of theta. Okay, and so the first term is something that's h of x doesn't depend on theta because t is sufficient by assumption. Whereas this second term, which I've written correctly here, it's just some gt of theta. It involves the data by the value of the statistic only, the t, and it clearly still depends on theta. And we've shown the factorization with the likelihood as h of x times gt of theta, and this holds because we assume that t was sufficient, thereby finishing the proof of the Neyman-Fisher factorization criteria. Any questions on that second proof there? Okay. Why was this important? It enables us to find sufficient statistics. I can write the likelihood, then I look at this form. If I can find something in this form, then I say t of x is my sufficient statistic, and then it can derive my sufficient partition because they're sort of derived by the sufficient statistics. All right. We also spoke about trying to find the most or the greatest amount of data reduction. And what we can do is we can look at many sufficient partitions. Okay, they're not unique. Right? As someone already said, you can look at the whole sample as also a sufficient statistic. Or this t of x is sufficient if it satisfies the Neyman-Fisher factorization criteria. So they're not unique statistics, the sufficient statistics, or the partitions. And so what we can do is we can order the sufficient partitions by the coarsest partition, i.e. the one that contains the smallest number of sets. Because you have the smaller number of sets, you have the greatest amount of data reduction. Okay, and so the partition or the sufficient partition that has the smallest number of sets, we call that minimal sufficient partition. Okay, because it has the greatest amount of data reduction. Okay, which is of course what we're looking to do to make our decisions easier. Greatest amount of data reduction. And to see that they're not unique, here's a neat little proof. So let's suppose that t is sufficient for theta. And now I apply some transformation g1 on this u function. Okay, so t is just some function of this u of x, where u is just some other statistic. Okay, there's another statistic, and g1 is a known function. Well, it can be seen that u must also be sufficient for theta. Okay, so if t is a function of some other statistic, then that other statistic is also sufficient for theta. Why? Well, it's just a direct application of the Neyman-Fisher factorization criterion. This is my likelihood function. Because t is sufficient, we can write it as gt theta h of x. Then I know that t of x equals g1 of u of x, where I know what g1 is. So I just substitute that in for t. Now I can just call g bar, can just be g of g1. Okay. So I'm just making a new function. The g1's known and g's known, so this is the function of two functions. Call it g bar. And again, I now have the Neyman-Fisher factorization criterion with the statistic ux, just a different g function, right? G doesn't have to be unique, it's just any function. And so u of x must also be sufficient for t. And u of x will have at least a less than or equal to dimension than t of x. Okay, so it has not a bigger number of sets than induced by t. Okay, it could have the same, or it could have a smaller number of sets in its partition. And that sort of helps us find minimal sufficient partitions. Yeah, so as I said, generally speaking, U induces what you could say finer, or at least no coarser partition than T. Since, for example, it might happen that U1 does not equal U2, but yet G of U1 equals G of U2. Thus, a finer partition of any sufficient partition is sufficient. That's the key thing. Okay. Thus, a finer partition of any sufficient partition is sufficient. Okay. So when we're doing our inference or applications, we're looking for the coarsest partition that is still sufficient. Okay, because we don't want to lose information on theta, but we want it to be the smallest number of sets as possible, or the lowest dimension if I'm talking about my sufficient statistic. Okay, because then we have the greatest data reduction without losing information about theta, right? And that's the goal. That's why we're doing this. Okay, and so we see that the statistic that introduces the coarsest partition will be a function of any other sufficient statistic, because we can just write it in this particular form here. Okay, and it can be a function of any other sufficient statistic. And then we call such a statistic the minimal sufficient statistic. Okay. And so we'll also look at strategies to find minimal sufficient statistics. Okay. Right now we've only seen how to find sufficient statistics. We'll also see how we can find minimal sufficient statistics as well. So let's just sort of recap some of the key properties we have of these sufficient statistics. If t is sufficient, then any one-to-one function of t is also sufficient. We've sort of just proved that, since it generates the same partition. If t is minimal sufficient, it is a function of all other possible sufficient statistics. Again, we just showed that. And the key thing, I guess, is that if t is sufficient, then this conditional probability does not depend on theta. Okay, the observed t is a summary of x, right? Because t is just a statistic, just a summary of the sample, but this summary contains all the available information about theta in its number. Okay, under the given family of models. Okay, it's also model dependent. Right, and it divides the sample space script x, which we've discussed, into disjoint sets AT, each containing all possible observations x with the same value of t as we've discussed. I always do that plot, right, where we have x, and then we split it into different sort of subsets. And if they all are here, they all have the same sufficient statistic, right? They all have the same value, t of x, for all x in this sample, or in this set, sorry. All right, let's do some examples of finding sufficient statistics. Let's actually apply these theorem that we just proved. All right, so here's 4 common distributions: the Bernoulli, normal, uniform, and multivariate normal. That should be a mean mu. I'll fix that up. We're asked to find the sufficient statistic and provide justification why that is the sufficient statistic. And there's a few slides after this that are going to help us solve some of the problems. All right, let's look at the Bernoulli case first. which has sort of been our go-to example so far. All right, why was this sum of the observations sufficient in the case of the Bernoulli? We showed why, but let's see how we can actually come up with it. So this was the first example. So for the Bernoulli, what do we know? Well, we already said that t equals the sum from I equal 1 to n of xi is sufficient. We proved this from definition to be fair, but we can directly apply the factorization criterion, which directly follows from doing the following. We write down the likelihood, Lx, parameterized by theta, right? And what is it? Well, it's just the product from I equal 1 to n of the probability mass function for Bernoulli, which is theta xi, 1 minus theta to the 1 minus xi. Now I can apply this product. I'll have the sum, or theta to the sum from I equal 1 to n of xi into 1 minus theta n minus the sum from I equal 1 to n of xi. And if t is the sum of the xi's, I can just write this as theta to the power of t, 1 minus theta to the n minus t. Okay, and you can see this expression only depends, so theta only depends on my sample through t. Okay, so this whole function is like my gt of theta, essentially. H of x can be set to be 1 in this case. Wherever we have a theta, it only depends on t. So theta only depends on my sample through t, and so t must be sufficient for theta in this example, and we define t to be the sum of the xi's. Okay, so I guess if we want to be more specific for this first example, so this likelihood involves the data only via the value of t. Okay, where we've defined the value of t to be the sum from I equal 1 xi t. So the whole right-hand side of this equation is my gt theta function. So the whole right-hand side can be thought of as gt theta. Okay, as I said, it was just theta to the t, 1 minus theta to the n minus t. And we can simply set h of x to be the constant 1. Okay. And that's it. There you go. We've just shown that t, which is the sum of the xi's, is sufficient for theta in the case of Bernoulli observations. All right, tick. Next one, univariate normal distribution with, oh, sorry, yes, questions. I should always ask for questions first. I think that may have been you who zoomed in. I think you got to click the top left or something to unzoom. Okay. Now, next case, let's look at a univariate normal with unknown mean mu and variance sigma squared. For this, we actually need a little help, and it's called the fundamental equality, at least in the one-dimensional case. And what it says is the sum of the squared deviations from mu, so the sum from I equals 1 to n of xi minus mu squared, well, we can rewrite this as the sum of the squared deviations from the sample mean plus n times the sample mean minus mu squared. Okay, so we're going to use this property, and the proof is quite neat, and again it follows from that idea of adding nothing. So if I look at the sum of the squared deviations from the true mean mu, well, I can add and subtract x bar, which again is just 0, right? I've added nothing. And I can treat this as my first term and this is my second term. The question is, why is hx equal 1 in the previous example? Because this likelihood has to be written as a g of t theta times h of x. And this whole thing here is my likelihood, but this whole thing is also gt theta. So I have to just set h of x to be 1. to fully specify this composition of the likelihood into gt theta h of theta, because the whole likelihood is just this, and the whole of g equals this. So I just have to set h of x to be 1. Okay, so this is my a squared. So this is my a squared. My b squared is this guy, and then we have 2ab in the middle. Now, this part in the middle, this doesn't depend on I, right? X bar doesn't depend on I, and mu doesn't depend on I, so I can bring it outside the summation, which is what I do here. And now here I have the sum of the xi's minus x bar. So if I expand this out, what do we get? Well, we get the sum of the xi's minus, now if I play the sum to x bar, I have x bar minus x bar minus x bar n times. And so it's minus nx bar. And so I have the sum of the xi minus the sum of the xi's, because, well, x bar and x bar is n times 1 over n, the sum of the xi's. Well, these two n's cancel, and it's just the sum of the xi's. And that expression becomes 0. So that guy becomes 0. 0 times a constant is simply 0, so we can forget about it. And so we're just left with these two decompositions that we have in the proof. And again here, this doesn't depend on I, so I just sum this n times, and that's why that becomes n times x bar minus mu. Okay, so that's the fundamental equality, and we're going to apply this for this sufficiency example in the normal case. Okay, so second case, and again, we're just going to follow the same strategy of write the likelihood and show we can factorize it in that form. So here, we're assuming we have normal population with mean mu and variance sigma squared. So here, my parameter, my theta, is two-dimensional, mu and sigma squared. Okay. Then the first thing we do is we always write down our likelihood. Lx of theta, and as always, it's a product from I equal 1 to n of the density of a normal, which is 1 over the square root of 2 pi sigma squared, the exponential of minus 1 over 2 sigma squared, xi minus mu squared. All right, that's my likelihood. And I can apply this product to this expression. The constant out the front becomes 2 pi sigma squared to the minus n over 2. And we have the exponential product of exponentials. The exponents become a sum. And so we get this summation type expression in the numerator. What is the definition of x? I'm only using xi's here. Oh, x bar. X bar is the sample mean. Yeah. So this guy is the sample mean, which means I go 1 over n times the sum of the observations. That's what that guy is. All right, now I'm going to apply the fundamental equality, because this expression here is exactly this expression on the left-hand side. And so I'm going to replace it with these two expressions here. Okay? So all I'm going to do in this next line here. So I have 2 pi sigma squared minus n over 2, the exponential of minus 1 over 2 sigma squared. Now apply the fundamental equality to this expression here. I get the sum from I equal 1 to n of xi minus x bar squared plus n times x bar minus mu squared. Okay, so that's apply fundamental equality. Okay. Is that the same as mu? No, mu is the population parameter we're trying to estimate. X bar is a random variable. Okay, it's the random variable of my observations, so sum of observations dividing by n, and then you have the observed sample mean, which is little x bar, which is actually collected from my data. Okay, so this is prior to collecting observations, and then this is actually collecting my observations, little x bar. Okay, now my parameters, where are they? Well, I have a sigma squared here. Well, there's no x, so that doesn't really matter. I have a sigma squared here, and so it depends on x through this expression here, and well, this x bar here. Okay, so they're the two. So this is one statistic, and here is my second statistic, in which my likelihood depends on both my sample, some suitably defined statistic, and the parameters. Okay, so this likelihood involves the data. I will get to the questions in a second. Via the statistic t, which is now two-dimensional because it depends on two separate statistics. And these two statistics are, well, this is my first one, which is just the sample mean x bar. And then also this second statistic, which is the sum of the squared deviations from the sample mean. Okay, so it only depends on these two statistics, right? This guy here and this guy here. All right. Oh, the question was just confirming. All good. Okay, so again, if you want to write out your two functions explicitly, because you want to write your likelihood as gt theta times h of theta, my gt theta in this example is, well, this depends on theta, because theta is the second component of theta is sigma. So it's 2 pi sigma squared minus n over 2. The exponential of minus 1 over 2 sigma squared. That's my T2. And then I have plus n into T1 minus mu squared. Okay. So there's my GTF function, but this is the whole likelihood. So again, my h of x can just be 1. This will not always be the case, but here again, it also just takes the value 1. Okay, because my likelihood is all of gt theta. This whole expression becomes gt theta. Or you could chuck in a 2 pi if you wanted to. You could take this 2 pi and put it in here. It would still work. Okay, it's just up to convention. It's any function g and any function h, such that you can write your likelihood into this form. Yeah. Any questions on that one? I guess I should also mention you could do any transformation of your statistic and it is also sufficient. All right, so in this example, remember t here is my sufficient statistic. Okay, so maybe make that clear. Hence, this two-dimensional vector, right, because it has two components, which we can call a vector statistic, I guess, is sufficient for theta. Okay, it's always good to say what we just shown, where theta has two components, mu and sigma squared. As we said before, we'll make a note of this, I guess. Every one-to-one transformation, one-to-one transformation of t is also sufficient. So you might be able to think of another statistic which is sufficient for t. So I guess if you want to look, we can look at one, just so you can see what's happening. Let's call it t tilde. Again, we still need two components, so we'll call that t tilde 1 and t tilde 2. So where's most of there? If I know x bar, I can times that by n and I get the sum of the xi's. And so I can say that the sum of the xi's is also a part of my sufficient statistic. And then if I look at this second term, if I expand this out, well, I get the sum of the xi squareds minus 2 times x bar plus the sum of the xi's plus x bar squared. And so the only thing that I don't have left, because I already have the sum of the xi's, is the sum of I equal 1 to n of xi squared. Okay. If I know these two expressions, I know these two expressions, and vice versa. If I know these two, then I know these two. Okay. And so it's a one-to-one transformation. And so this statistic, t tilde, is also sufficient for theta. For theta, since knowing t, which is the two components t1 and t2, we can recover, or we can get back my t tilde 1 and t tilde 2. And vice versa, you can also go the other way as well. Okay. Any questions on that exercise? Oh, there's one. Why is t1 equal x bar and t2 equal the summation expression? That's because we can write the likelihood as a function of gt theta times h of theta. Right, that comes back to this expression. Now, the only time I see my data is in x bar here and this expression here. So I replace that with t2, I replace that with t1, and now my likelihood can be written as gt theta times h of x. Okay, where t is these two components, t2 and t1. All right, we'll take a 5-minute break. We'll come back at just a bit past 7, and we'll go through the other two examples, which are again going to be slightly different to the one we just did then. Yeah, sure thing. I'll move it. All right, let's have a look at another example. So ticked off the normal. Now let's look at a uniform distribution in 0 to theta. Now the uniform distribution is slightly different in the sense that the support of the distribution depends on the parameter. All right. So I know that the values of x must lie between 0 and theta. And so if I change theta, I change the range of values for x. Now this is not true for, say, the uniform, for the normal, because I know it's over the whole real line. Or if I'm in the exponential, I know it's all positive values, irrespective of the parameter. So the uniform in that regard is a little bit different because its support depends on theta. So we'll have to be a little bit more careful in the uniform case. But the same strategy is still going to be viable for this example. All right, so we have our n observations, x1 to xn, our IID uniform over the interval 0 to theta. All right, first I'm going to state what I think is going to be a sufficient statistic, or all that I know, and that is that it is t subscript brackets n, which means the nth order statistic. Okay, we will have a chapter on order statistics, but basically here it's just the maximal of the n observations, and we call it the nth order statistic. But you can speak of the first order statistic, the second order statistic, which are just the smallest and the second smallest, and so on and so forth. Okay, so this is the nth order statistic, or in this example, equal to the maximal of the n observations. And that kind of makes sense to be sufficient. Maybe I should say it's sufficient for theta, because theta is the upper point of the range 0 to theta. So the largest x tells me the most information about theta. And in fact, it tells me all the information I can possibly gather about theta based on that sample. Okay. We want the likelihood, but before we jump into the likelihood, let's look at the density of the normal. Okay, so the density can actually be expressed using indicator functions, and then we're going to use a little neat property of these indicator functions. It can be expressed using indicator functions. So my density for a single observation, parameterized by some value theta, well, we know it's uniform from 0 to theta, when the area under the curve must be 1, so it's 1 on theta, and we know that theta must be bigger than x and can go anywhere up to infinity. Where here the indicator function, so this I x comma infinity theta, it takes the value 1 if theta is in x to infinity, or it takes 0 otherwise. Okay. So it says if this guy here is in this set, then take the value 1, otherwise just take the value 0. I guess we can draw this density. I've done it before. Right? If this is f of x theta, well, this has to be 1 on theta. Theta will be some parameter here, takes this value, and otherwise it takes the value 0. Okay. The first step is to come up with my likelihood function, and it's just a product of the density functions given by this expression here. 1 over theta, the indicator, now the x becomes xi to infinity of theta. Now, 1 on theta is a constant, multiply that n times, I get 1 over theta to the power of n. Now, the second term, I'm going to write it like this first. So it's the sum from I equal 1 to n, the indicator, that xi to infinity of theta. So theta only takes the value 1 if, this expression here only takes the value 1 if theta is bigger than xi. Okay. Now this is a product. If there's 1 0 in this product, the whole thing is 0. So it's only going to be 1 if all of them are 1. Okay, they all have to take the value 1, otherwise this guy is just 0. And when are they all going to take 1? Well, we need theta to be bigger than xi. So theta has to be bigger than x1, bigger than x2, bigger than x3, all the way up to xn. So I can write this as 1 over theta to the power of n, the indicator that it is also bigger than the maximal of the n observations. Okay, it has to be bigger than each xi. Well, that means it has to be bigger than the biggest, because if it's bigger than the biggest, it's obviously bigger than all the rest. And then what I can do is I can just multiply this expression by 1 to get your h of theta. So I can write this as g of xn theta times h of x. So h of x is 1, and g x n of theta is, well, this guy here. Okay. And again, we have the likelihood factorized in some way, and so the statistic here must be sufficient, and the statistic here is this x subscript in brackets n, or the nth order statistic. Okay. So again, what we've kind of been doing, this likelihood represents a factorization, right? That's what we're doing. And so the statistic t, which equals the nth order statistic, the largest of my samples, sorry, must be sufficient for theta. Okay. Any questions on that exercise? This is something that will happen a little bit when you do see the support of the density depending on the parameter. You will see that this indicator will have a role to play, not just when looking for sufficient statistics, but also when we're deriving MLE and looking at other quantities throughout the course. It is something that is important. So if you ever see the support depend on theta, then you need to be a little bit more careful than you otherwise usually would. Okay. And the final example is looking at a multivariate normal distribution with unknown mean mu and variance covariance matrix given by sigma. Now again, we need some useful formula here. So we can extend that one-dimensional fundamental equality into a p-dimensional fundamental equality. And it takes the same form. It takes the sum from i1 to n of xi minus mu times xi minus mu transpose now, which kind of plays the role of the sum of the xi minus mu squared. Well, that equals a contribution from how far xi is away from its mean, sample mean, plus n times how far x bar is away from the true mean mu. Okay. So here x is now a vector, right? So this is like the mean vector for each of the p components, and each xi is p-dimensional, right? So each xi here, right, it's like xi1, xi2, all the way down to xip. Okay, so it's a p-dimensional. Okay, we're talking about random vectors here, so it's a distribution on that random vector. And we also need a property of the trace function. Okay, so just remember what the trace does. Right, the trace, which we call TR, is just the sum of the diagonal elements. And so if I have this X transpose AX, where A is just some matrix, where all the matrix multiplication is properly defined, well, X transpose AX can also be written as the trace, so the sum of the diagonal elements of the matrix found by taking A and applying XX transpose. Okay, so we're going to use that in our derivation for the sufficient statistic in this case. Okay. What is this? Exercise number 4. So now we're looking at multivariate normal. And as I said, we're looking at p-dimensional random vectors. Okay, so each of my xi is distributed according to a multivariate normal with p dimensions with mean vector mu and variance covariance matrix sigma. Okay, so mu is kind of what we had, right? Mu1 all the way down to mu p. And then the sigma matrix is like that sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2, and so on, down to p dimension. Okay. What do? Well, we write the likelihood. This now depends on two parameters, mu and sigma. And they have p components in mu and p times p, I guess, divided by 2 in sigma. Okay, so we've got many parameters here in which we want to estimate. Now, my likelihood is, again, as a product of the density of these multivariate normal vectors. It looks similar to the univariate case, although extended slightly to handle the multivariate context. Here it's the determinant of the variance covariance matrix to the power of -1/2. And then we have this exponential part, which takes a similar form, xi minus mu transpose times the variance covariance matrix inverted into xi minus mu. Now we can apply this product to the constant, similar to before. You get 2 pi to the power n minus np over 2. This is also just a number, and so we have to multiply it n times. You get that expression there, and then multiply a bunch of exponentials. Well, you can just sum their exponents. And we can do the same thing here, where the summation is going component-wise. Xi minus mu transpose, sigma inverse xi minus mu. All right. Now, what can we do? So this can still stay the same. Remember, we're most interested where we see a mu and a sigma, okay, because that will tell me where my sufficient statistic may be lurking. Exponential of -1/2, the summation, and now I'm going to use my trace property. So here we have something transposed times a matrix times that same thing. Well, if we look back here, this is what we had here. We had something transposed times a matrix times that same thing. Well, I'm going to replace it now with this expression, where A is the variance covariance matrix and X is this xi minus mu transpose. So I can write this as the trace of now the variance covariance matrix inverted. So this is not a summation now. This is this variance covariance matrix into xi minus mu transpose. Okay, so that was the trace property. Now, there's one more thing we can do. We can apply our fundamental equality in this example. Okay, we have this expression, which we look on the previous slide, right? We can write this guy into these two separate terms, and that's exactly what I'm going to do. Okay, so this guy is just going to be replaced with this expression here. And I can swap the trace and the summation around because they're both linear operators. So you can do the sum and the trace, or the trace and the sum. It's the same thing. So I can reverse their order around as well. So these are all my constants. Nothing can change with these guys. Then I have the exponential of -1/2. And as I said, I can take the trace out and swap it with the summation signal. So I can put the summation guy inside, and I'll leave it inside the actual expression. I should. So here, that matrix inverted, and now I can do the summation sign because obviously this sigma doesn't depend on I, and so I get xi minus x bar into xi minus x bar transpose, and then the second term from the fundamental equality, which is this expression here. Now let me get my brackets right. So that goes with that one. Then we have a square, and then finally cut off the exponential. Okay. So yeah, I'll make a note here that the trace and the summation are linear operators and can be interchanged. And their order can be reversed, I guess. Okay. And now you kind of see similar to the univariate normal. Okay. Again, we're looking at our parameters. My parameters here, mu, well, that only is multiplied or as a function of x bar. And then here, well, you see you have a sigma inverse, which is a parameter, and it only depends on the observations through this statistic here. So again, we can have that decomposition of my likelihood as a function of x bar and this summation of xi minus x bar into xi minus x bar transpose. Okay, so again, my likelihood, which depends on these two parameters, involves the data only via the statistic T1, which I'm just going to call x bar, and the statistic T2 will be that guy there, which is the sum from I equal 1 to n of xi minus mu into xi minus mu transpose. Okay, so what we can have is that hence that T equals T1, T2 by the factorization criterion is a sufficient statistic for mu and the covariance matrix. Okay, so this one was a little bit more involved. This was really on the challenging end of the exercises, and there were some properties that we had to use along the way, such as the trace property and also this fundamental equality. So if you ever had to do this in an assessment, it'd be more an assignment problem than anything else. I would also give you these as hints to help you along the way. For an exam problem, I think this is a bit too challenging because there's a lot going on. But the reason we do this exercise is to show that this can extend to even more difficult cases, okay? Because the first three were very straightforward cases, and this one was, in the multivariate context, a little bit more challenging and maybe more applicable to real life data when you have sort of multivariate normal observations. But is there any questions on any of those exercises or that last exercise that you'd like some clarification before we move to constructing minimal sufficient statistics? So the question is why x bar becomes mu. It doesn't. X bar is a random variable, right? It's the sum of my observations divided by n, right? X1 has a multivariate normal distribution. I don't think I've written anywhere there that x bar equals mu. Mu is a parameter, it's a fixed number. I still don't know what you're referring to. This says, therefore, the likelihood involves the data only via the statistic T1, which is x bar, and T2, which is this statistic here, the summation from I1 to n, xi minus mu times xi minus mu transpose. Hence, T is a sufficient statistic for mu and sigma. Okay. All right. So now we know how to find sufficient statistics by looking at this factorization criterion of the likelihood function. But we're in search of the greatest amount of data reduction, and so we want minimal sufficient statistics. Okay, I made an error there, did I? Thank you. You must have glanced over. Yes, of course. Yes, thank you. Sorry about that. Yes. Of course, the statistic can't depend on the parameter. That wouldn't make any sense. This guy I wanted to copy down. Thank you for that. I appreciate your attentiveness. Yes. Sorry. I thought you said I wrote something like mu equals x bar. Sorry, there we go. Yes, of course, statistics can't depend on parameters because you want to compute it from your sample. Okay, so yes, it can only depend on x. Good pickup, thank you. All right, so we want the greatest data reduction possible. And so the method to do this is the Lehman method. Okay, and we're going to find sufficient statistics using this method, but it turns out that usually if you find it using the factorization criterion, it's going to be minimal sufficient. For example, if we look back, maybe not that example, this example, t equaled the maximal of my n observations. So it was one-dimensional. This statistic is one-dimensional. And you can't get any more data reduction than being one-dimensional. So this would be the minimal sufficient statistic for a bunch of uniform random variables. If I come back to, that's two-dimensional. If I come back to this example, the sum of the xi's is sufficient. Again, that's one-dimensional. It's just one number, the sum of the xi's. And so the summation of the xi's is also a minimal sufficient statistic for the Bernoulli. But of course, we want to find a way in which we can do this generally. But once you find a sufficient statistic and its dimensions is 1, which is as small as it can get, it's in fact minimal sufficient. But how can we find a general procedure to come up with minimal sufficient statistics? Here it is. Here is the theorem. So remember, we talk about sufficiency by some partition. So we're going to speak about minimal sufficiency in a similar way. Let's consider a partition script A of my sample space script X, and we're going to define the following sets. For X in my sample space, I'm going to define the set AX to be the points Y such that Ly theta divided by Lx theta does not depend on theta. Okay, so I've got two samples, Y and X. I'm going to fix X. Then I'm going to look at the ratio of the Y sample likelihood divided by the X sample likelihood. And I want to find a statistic, such that I can set Tx equal to Ty. And then this whole ratio won't depend on theta. Or this ratio is a function of only Y and X and not theta. Okay. Then the sets that are defined by this AX, for X in my sample space, will form a partition of my sample space, and this partition is minimal sufficient. Okay, so I look at this likelihood ratio of a Y sample and an X sample, and I want this ratio not to depend on theta. So the sets that define this expression not to depend on theta turn out to be the sets that define my minimal sufficient partition. Okay. So again, we're just computing a likelihood of a Y sample and X sample, compute this ratio, find the situation in which this won't depend on theta, and we'll look at some examples on how you do that by defining a suitable statistic, and then that statistic will generate your minimal sufficient partition. Okay, so the proof is given in the notes. I'm going to bypass the proof because it is quite subtle and a little bit elegant, and we're sort of pressed for a bit of time, so it's in the notes for the discrete case only. And if you guys want to have a look at going through this proof, and you can ask some questions on it later, but for the sake of this course, I'm not going to examine it nor go through it during the lecture. But there's three things to do essentially. Firstly, you have to show that the sets AX defined in this way, first that they actually define a partition. Then you have to show that they actually define a sufficient partition. And then third, you have to show that they define a minimal sufficient partition. Okay, so there's three things you have to do there. And they're all outlined in these 4 to 5 pages. But as I said, I'm going to skip over it for the sake of this course. Okay, how can we come up with these minimal sufficient statistics? Well, let's apply this to 4 different cases. Again, the Bernoulli, the normal, and the uniform. And I'm going to substitute out the multivariate normal for the Cauchy distribution because I think it's a rather interesting case to look at. Okay, so let's start with the Bernoulli and let's show that T has a minimal sufficient statistic, and let's see if we can find it. All right. Exercise 315. So our first case, well, this is the Bernoulli case. What do we want to do? Well, first, we're going to take two independent samples of n tuple of data, so n observations. Okay, let's call them x, which is just x1 to xn. And my second sample, which is independent of the first, and we'll call that y, which is y1 to yn. Then, looking back at the definition, back a bit, we want to look at this ratio. And we want to find when this ratio does not depend on theta. All right, we've written the likelihood before, so I don't need to write it again, as we did on the previous exercise, but now we can do it in the terms of looking at saying when this ratio doesn't depend on theta. Now, the likelihood of the y sample is just going to be this expression, n minus the sum of the yi's. And for the x sample, well, it's going to be the same thing, except it's the sum of the xi's. All right, so remember I want to find a statistic such that tx equals ty, and then I'm going to get some cancellation for the thetas. Now, what I can do, when you have a minus, it can go into the denominator, and this minus will push it to the numerator. So I can actually write this as theta over 1 minus theta, and then here I'll have the sum of the yi's minus the sum of the xi's. Okay, because this minus will make this 1 minus go to the bottom, and then I keep this minus here because it's already minus. And the 1 over theta to the n will cancel on both sides, right? This n will cancel with this n. Okay, and this minus will just flip that to the bottom, and then you get this expression here. Now we want to define our set such that this expression here does not depend on theta. And it's quite direct now what has to happen, right? So for this not to depend on theta, right, because this is the ratio which defines our sets, and we want it to be independent of theta. So to not depend on theta, well, what do we need? Well, we need the sum from I equal 1 to n of yi equal to the sum from I equal 1 to n of xi. So when this holds, that defines my sufficient partition, or my sufficient statistic. Therefore, t, which equals the sum from I equal 1 to n of xi, is the minimal sufficient statistic. Any questions on that example? And if I guess if you want to talk about sufficient partitions, well, what you would say here is that T defines the sets in the minimal sufficient partition. They're sort of the contours of the statistic Tx equals the sum of the xi's, if you want to talk about sufficient partitions. But generally speaking, a sufficient statistic is what we'll be dealing with most of the time. Okay, because when these two are equal, right, this is like theta 1 minus theta to the power of 0, which equals 1. So it doesn't depend on theta. That's why we chose this, because then this is 0, and then this likelihood ratio doesn't depend on theta. Cool. Second example. Normal with unknown mean mu and variance sigma squared. Okay. Again, we want to apply exactly the same strategy as we just did. So again, we're looking at some normal data with mean mu, variance sigma squared. My parameter mu, theta, is mu and sigma squared. We compute this ratio again, assuming we have two independent samples of size n, a y sample and an x sample. Then again, we can compute this ratio of the y sample and the x sample. So the question, based on the previous question, was how was the formula derived, theta over 1 minus theta? It's just algebraic manipulations, right? It directly follows from this, right? Because this is minus the sum of the yi's, it goes to the bottom, right? And then to make this one go to the top, you could just put a minus there, and that's where that minus comes from. And this is just the ratio of two likelihoods, right? That's the likelihood of my y sample, that's the likelihood of my x sample. The ends cancel, and that, because that's a minus, it goes to the bottom, and to make that go to the top, you put a minus, and that's how you get this theta into 1 minus theta. Awesome. All right, now normal, again, we computed this likelihood previously, so we can just directly write this likelihood of first my y sample minus 1 over 2 sigma squared. So I'm going to expand the brackets. So the likelihood we computed before is here, this expression here, okay? Now what I'm going to do is, straight away, I'm just going to expand this guy. So I'll have the sum of xi squared minus 2 times mu times the sum of the xi plus n mu squared by expanding this guy and performing the summation. So I'm going to start with doing that straight away. Okay, so we'll have the sum from I equal 1 to n of yi squared minus 2 mu, the sum from I equal 1 to n yi plus n mu squared. And we'll have the same thing for my x sample. Okay, and except you just replace y with x. And again, I'm going to expand it out in the same way. So we'll have xi squared minus 2 mu, the sum of xi, I equal 1 to n, plus n mu squared. All right, let's do some cancellation. Maybe I'll see if I can change color. Or will it change everything? Oh, that's fine. Okay. This cancels with that. They're just constants, because sigma squared is the same value for both samples. Okay. This will cancel with this guy here, because again, they're just constants, so they're going to cancel. And now I just have a ratio of these two expressions. Oop. Okay, so keeping my form and forgetting everything I've moved, and because this is minus, if I bring it to the top, it'll become positive. Okay? Because 1 over e to the minus x is e to the x, right? So that's all I'm doing here, except x is playing the role of this big expression. I'm going to keep the 1 over 2 sigma squared. So what do I have? I'll have the sum of the y squareds first. And then this guy, because it's going to the top, will now be minus. So minus the sum from I equal 1 to n of xi squared. Minus 2 mu into the sum of the yi's. And this guy is on the bottom, make it to the top. So this will be minus. Here, minus minus makes this plus when it goes to the top. The sum from I equal 1 to n of xi. Now I want this ratio not to depend on mu or sigma squared. So what do I need to do? I've done it again. Well, I need this to be equal to 0, and I need this to also be equal to 0, because then it won't depend on mu here, because that's 0, and it won't depend on sigma squared here, because, well, this whole expression would therefore be 0. Okay. Oh, sorry. All right, so let's write that more expressively. And so for this to not depend on theta, and so we can create our minimal sufficient partition. Well, we need the sum of the xi's to equal the sum of the yi's. And we need the sum of the yi's to equal sum of the xi's, the sum of the yi squares equal the sum of the xi squared. Oh, sorry, that should be just one big bracket, right? It's a vector. I need the sum of the xi's to equal the sum of the yi's in the first component, and the sum of the xi squareds to equal the sum of the yi squareds to hold. Okay, and so hence my statistic t, well, in the first component, it's the sum of the xi's. In the second component, it's the sum of the xi squareds. And this is actually the one we found previously when we did our sufficient statistic. It's exactly the same that we found. Although it was a one-to-one transformation of the one found using the factorization criterion, but we wrote it out explicitly. So that statistic is minimal sufficient for theta, where theta is my two parameters, mu and sigma squared. And of course, as I said previously, as is any one-to-one transformation of t. Okay, again, minimal sufficient statistics are not unique. Okay. And we saw a previous one looking at x bar and the sum of xi minus x bar squared. Well, that's also minimal sufficient because it's also of dimension 2. So it has the same dimension. We know it's sufficient, so it must also be minimal sufficient. All right, any questions on that exercise? Okay, the third one, take these off as we go. Uniform. Now we're going to get tricky again by applying this idea because, as I said, the likelihood is going to be a function of these indicator functions. And so it's going to be a little bit more tricky than the previous two. Okay, but we're just going to use our previous definition that we had before. Okay, so, oops, sorry, I'm freezing here. Okay, my observations, x1, x2, up to xn, we're going to assume that they're uniform over 0 to theta. Now, as always, when we're looking for minimal sufficient, we look at the ratio of two likelihoods. Now, we wrote these likelihoods previously, so I'm just going to rewrite them here. It was 1 over theta to the power of n. The indicator function, that theta was bigger than the maximal of my n observations, of my y observations, I should say. And then on the denominator, it would be the same, 1 over theta to the power n. Now I want the maximal of my x observations. I want theta to be bigger than that. Again, we're using the same theta, so they're constants. And so this ratio is actually just an indicator function for my y sample and an indicator function for my x sample. Now it turns out this is independent of theta. We'll have to do a bit more working to claim this, but let me just write it down first. This is independent of theta. So that means it doesn't change. It doesn't jump from 0 to 1, even maybe to infinity, right? Because these take the value 0, 1. So you have sort of 3 possible values, or even not defined. This ratio could be not defined, and then it's sort of jumping around. So this is independent of theta if and only if the maximal of my n observations is the same as the maximum of my y observation, okay? Which implies that the statistic t equals the nth order statistic is minimal sufficient. Why can I claim such a thing? Well, let's take an example of when these two values are different and see what happens to this ratio. Okay, so indeed, if these two values were different, so x order the nth order statistic of x and y were different, we can consider two cases, right? The maximum of my x sample is bigger than y, or vice versa. Okay, I'll just do one case and leave the other case for you guys to consider, and it follows a similar strategy. And the case I will consider is, let's just suppose that the maximum of my x observations was smaller than the maximum of my y observations. Then let's see what happens to this ratio here. Okay. All right. We're going to move theta, right? Theta is the thing we're going to move. And remember, we want this ratio to be constant as theta moves. So we want to take the same value no matter what theta is. But let's see what happens if I move theta. So if theta was less than the maximum of my x observations, then what does this likelihood become? Then this ratio, okay. Let's make sure I get this right. Okay. I'm just going to swap these, because it doesn't matter what order we do them. So I'm going to call the top sample my x, that's why this was previously, and my bottom sample a y. Doesn't change too much, but it will for this ratio thing. Okay. So my x samples in the numerator, my y samples on the denominator. They're just arbitrary samples anyway. Okay. So now let's look at this ratio of the x sample likelihood to my y sample. Well, theta is less than the maximal. So this only takes the value 1 when theta is bigger than the maximum of my n observations. But here we're assuming it's smaller, and so it takes the value 0. Similarly, we want theta to be bigger than the maximum of my y observations, but theta is less than the maximum of my x, which is less than the maximum of y, so that is also 0. And so we have 0 over 0, and that's not defined. Okay, you can't take 0 and divide by 0. So when theta is less than the maximum of my x observations, this ratio is actually undefined. Now let's keep shifting theta along. So now let's move it, say, bigger than xn, but smaller than the maximal of my y observations. Then this ratio, Lx theta over Ly theta, what happens? Well, now it triggers the top indicator. That becomes 1, because now theta is bigger than xn. So that takes the value 1. But theta is less than yn, so the denominator does not trigger, and so that's still 0. And so this takes the value, well, generically speaking, infinity. 1 over 0. Abusing a lot of notation here is essentially infinity. And then finally, the final case, if theta is bigger than yn, so now it's bigger than both of them, then both of these indicators are going to trigger. And so they're just going to both be 1, and you have 1 over 1, which equals 1. So now I'm going to plot it. I'm going to plot this ratio. All right, so as I move theta, I want to plot the ratio of Lx theta over Ly theta. And remember, these are fixed. My maximum, my x, and maximum, and these are fixed because they're my observations. So we said when theta was less than the maximum of my x sample, it was not defined. So here, the function is not defined, which is fine. Okay, we don't have to consider this case. It's not defined. When theta was between the maximum of my x observations and the maximum of my y observations, it took the value infinity. And when theta was bigger than the maximum of y, it took the value 1. So you can see when theta is defined, it's not constant. This ratio is not constant as theta changes. It starts at infinity and then drops down to 1 when theta gets bigger than yn. Okay, so this clearly depends on theta. When it won't depend on theta is when x, maximum of my x, equals the maximum of my y. because then this gap in the middle is going to be removed, right? And then you'll just have something that's not defined here and then just takes the value 1. So where the function is defined, it's constant with respect to theta. That only occurs when x subscript n in brackets equals y subscript n in brackets. Okay. But also do the other case as well. So reverse this and say the maximal of my x is actually bigger than the maximum of y, and see how this ratio changes. And we only care where it's actually this ratio is defined. When the ratio is not defined, we can just ignore it. What was the previous point? I'm sorry, I don't know what that point you're referring to now. Okay. So yeah, I encourage you to do the second case. I'm not going to do it, but just suppose that now the maximal of my y observations happens to be less than my x observations, and then do the same sort of strategy. Okay. Yeah, and you'll see that in both cases, when the maximal of my x it does not equal the maximal of my y, the ratio Lx theta over Ly theta, where it is properly defined, still depends on the position of theta, i.e. it's not independent of theta or it's not constant with respect to theta. And so the conclusion to have the ratio not depend on theta and on theta, we need the maximal of my x observations to be equal to the maximal of my n observations. And so, as I claimed at the start, the maximal of the observations is my minimal sufficient statistic, as we found out using the factorization criterion. Okay, so 1 over 0 still has an interpretation in a limiting sense. Where you have a 0 divided by a 0, it's just not defined because there's no magnitude to zeros. But 1 over 0 can be defined as, say, infinity. Yeah, but 0 over 0, you don't know. It depends on how quickly it goes to 0 and things like this. Yeah, let's do one more example of finding minimal sufficient statistics. Probably the most interesting one of the, maybe the uniform was pretty interesting. And this is the Cauchy distribution. So this example actually shows that sometimes the dimension of the minimal sufficient statistic can still be quite large. And in this example, it actually turns out to be the same size as the sample itself, which doesn't really help do any data reduction at all. Okay. It's a V. Okay. Again, we have our IID observations, x1 to xn, and they're going to be independent and identically distributed according to the Cauchy distribution with some parameter theta. And its density function is given by the following. It is 1 over pi times 1 plus x minus theta squared. Okay, and it's defined over the whole real line. Okay, so this has really heavy tails. The Cauchy distribution has heavy tails compared to a normal distribution. Now again, let's look at the ratio of the two likelihoods of a y sample and an x sample. The pi's will cancel out because they're just constants. All right, so here you'll have a product from I equal 1 to n of 1 plus xi minus theta squared. And in the numerator, you'll have a product from I equal 1 to n of 1 plus yi minus theta squared. The pi's cancel and they're flipped. So here's y and y is down the bottom because it's 1 over. And so x is on the denominator here, comes to the numerator here. Okay, so this is the ratio. And not much else can be done. No further simplification can be applied to this ratio. Okay, and for it to not depend on theta, what do we need? Well, it turns out we need in this product, let's take I equals 1. We need x1, the smallest of the x sample, to be exactly the same as the smallest in the y sample. We also need the second smallest in the x sample to be the same as the second smallest in the y sample, so that they cancel out in this product. Okay, if you do some sort of permutation and order them from smallest to largest, we want this term to cancel with that on the denominator. And that only happens when all the order statistics match up all the way down to the maximal of the n observations. Okay, so this ratio doesn't depend on theta only if the order statistics are the same. Okay, and so that's it. That's all we can do. That's all we can say. Hence the statistic t, which is now my n order statistics, x2, x1, x2, up to xn. These are ordered from smallest to largest, is the minimal sufficient statistic. But it's exactly the same sample size as my observations to begin with, so we haven't done any data reduction at all. Okay, no data reduction is possible in this example for the case of the Cauchy distribution. Okay, all right, the dimension of my minimal sufficient statistic here is equal to the sample size, so virtually no data reduction is possible at all for my Cauchy distribution. Okay, again, the reason is that I want all the contributions from all these terms to pretty much cross out. So when this holds, right, if I do the smallest first, the indexes might be different, but what I want is I kind of want 1 plus x, the smallest, minus theta squared, and you have all of them, right, all the way up to 1 plus xn minus theta squared, right? And I'll do the same with the y's, 1 plus the smallest of the y1 minus theta squared, all the way up to 1 plus sort of yn minus theta squared. And then because these are equal, this cancels with this one, that one cancels with that one, and that one will cancel with that one. Okay, just the indexing here has to change to sort of match the order statistics, because here they're not ordered, and here I want them ordered. Okay. Any questions on that exercise? And as I said, right here you'd have a pi to the n, and here you'd have a pi to the n, and they cancel as well, if you just want to be fully complete with the solution. Okay. Done. Let me just bring up this important family for the last thing we discussed. We've got 2 minutes. This important family will give us a lot of the properties that we need to perform our procedures. So it's called the 1-parameter exponential family. And if you can show that your density belongs to this 1-parameter exponential family, then directly you can say that the statistic is minimal sufficient. You can say it's sufficient, and you can also say it's minimal sufficient. And there's actually some other properties that we're going to discuss later in the course that you can also assign to this statistic. Okay, which is just going to be a function of this D part here of this form. Okay, so if you can write your density into this form, so A times the parameter, a function of the parameter times a function of x, and then the exponential, a function of the parameter times a function of x, then we can say it's in the 1-parameter exponential family. And then we get a bunch of properties for free based on the back of this. Yeah, there's different forms for this 1-parameter exponential family. We're just going to stick with this expression here for this course, and we won't actually deviate from this expression. So this is the only exponential family form we need to use in this course. Yeah. So yeah, get used to this, and a lot of the distributions that we consider fall into this class of family, class of distribution. So from the exponential, Poisson, Bernoulli, normal distribution, there's a lot that fall into this family, and we will utilize this guy a lot. Okay, I guess we will leave it there. I've added the second set of tutorial problems up as well, which start to cover some of these ideas of sufficiency and minimal sufficiency. So there's plenty of examples in the tutorial problems that do additional examples of the factorization criterion, and also looking at the ratio of the two likelihoods and showing it's constant with respect to theta to derive our minimal sufficient partitions. All right, well, thank you for staying with me, and enjoy your weekend, and make sure we're working on that assignment. It's due next Friday, midnight. And yeah, enjoy your weekends. Thanks, guys.